So, dear students, here I'm trying to give you a recording about learning materials for our first week or the first task, let's say. And this is basically used to help you for your self-learning. So it serves kind of as an appetizer for you to get your deep learning phase, either during reading the book or during solving the tasks. All right. The whole recording will be about 30 minutes, I guess, and I try to keep it brief, but also covering a few important concepts to guide you to go to your deep learning phase. All right. The learning objectives for this week, actually, for basically the content related to task 1 are the 3 levels. Yeah, so the knowledge and understanding level, we want to give you the knowledge and understanding about the design phase, yeah, or design processes, and especially how do you use material indices or material index to serve your design processes. And the second point is on the skills and abilities. So we try to show you how to use the Granta EduPack to apply to, let's say, operations, screening, and ranking to basically select your materials. And of course, in a big picture towards the value and attitudes, we would like to make you feel the appreciation of design-led decision-making using the EduPack tools, especially with respect to material selection. Well, the reading materials are from our textbook, of course, and if you would like to read more, you're also referred to the second book listed here, and the corresponding chapters are also the same from 3, 4, 5. All right. And first, I would like to begin with the design process. So this is a chapter we didn't ask you read carefully or deeply at least, but I think it's a nice concept for everybody to know how a design of a product is made. Yeah, because after that, you're going to do the production and so on. So when you do the design of a product, the process actually begins with the identification of market need. And then we try to give a problem statement. I'm going to just slip over about these two things because they're not too relevant at the moment. What is more relevant for our course is these 3 steps in between. So the concept, embodiment, and detail. And after these 3 steps are finished, you have the product specification. Basically, this is something you can send a manufacturer to produce. Yeah, so what is all this about? I will try to explain you one by one. But before going to that step, you should actually already know at this early of the design phase, the material concern or material selection is already entering to the plane. So it's not just at the end, I decide what the materials I would do when I have the full plan of my product. Actually, it goes at each step. Yeah, the difference is at the concept level, well, you need to think more about the material family. So you don't need to be specific. But when you go to embodiment, when you go to detail, you should go to the second level, the third level of details of your material properties. All right, now let's just go to these 3 steps one by one. And so what is concept? So we first get the market need, yeah? So here I'm giving you an example about need. So this is basically we have our wine stored in a corked bottle, yeah? So you want to get your wine out. The need is to open the cork, right? You want to get a removal of this so-called cork. And the concepts are, yeah, several. I just list a few, which are basically existing in the market. You probably know this. This is the first one, yeah. because the bottom line for this concept is we need to apply tensile force in the end to remove this cork. Yeah, the first concept is just use screw. Yeah, you screw in and then you just tensile out. And second is using sharing, right? And then you tensile out. And the last one is a little bit interesting. So you try to just increase the inner pressure of your bottle, and then that pressure will automatically just open the bottle. Yeah. So actually for wine, you know, the most used is the first concept from daily life, because they're dominating the market basically. But actually, this is also an interesting and a common to see concept. Yeah, not for wine, but in a way applied to champagne, for example. Now we have our concept. We have chosen the first one, and now we can move forward with embodiment. So basically, during embodiment, we need to detail already a little bit. Basically means how we're going to realize this concept. So here I'm listing two. So the first is direct pull. Yeah, this is the one basically we're using actually for most of those tools. And the second is lever pull. Yeah, that's an interesting concept. And of course, you can have other creations to really try this out. Here I'm going to show you how the second embodiment could be moved further. Yeah, when we have chosen this kind of embodiment, and we can already decide how to do the detail. Yeah, when you do the detail, basically it means you need to identify the dimensions. Yeah, so we know the general looking of this embodiment. In detail, we need to give dimensions. So here it involves a lot of design things. But if we just go to the point of material selection, and we need to actually get those two things out. So basically here we have a handler and we have an arm. Yeah. So as you can see, finally, we decided to go with a certain material and through certain processes to produce this item. And this is for the grip and this is for the arm. So the question here for our lecture, really, basically for you guys, is how did we arrive from the detail part into those two decisions? Yeah. And this course basically, or this task for this week is gave you some basics. So you will learn the methodology in general. You cannot probably learn the whole thing at once, but you will learn the general methodology, and you will be also getting tools and ideas how to do some simple material selections. All right, now let's move to the main content of today's course. Basically, how do we do the material selection when we have a design detail? And this generally involves 4 steps. Yeah, so I'm going to show you those steps first in a general and then one by one. So the first thing we need to do is to do a so-called translation. Yeah, this translation is basically we need to get our design requirements and express them into constraints and objectives. So here I show you what they really mean. So constraints means some yes or no requirements. For example, yeah, are the materials needed to be molded? Yeah, so meaning we have to be able to use the material to be molded if needed, yeah, or doesn't. And second, like if the material should be waterproof or water resistant, yeah, yes or no. And this is the first type of constraint. And second type is just a kind of a threshold. It's a quantitative measure, yeah. But you don't need to really do, let's say, optimization. You basically just need to fulfill a certain lower bound. Yeah, for example, the material should be stiff enough, meaning the stiffness of the material should be just above a certain level, or the material should be strong enough. So that means the strength should be above a certain level. So all of this are the so-called constraints. And the second thing It's called objectives. So the objectives are measured actually by quality. Yeah, measured by quality, not meaning just a threshold, but actually we're gonna need to optimize it. So optimize means we either minimize or maximize. So the typical objectives are as cheap as possible, yeah, as light as possible, or as stiff as possible. So we don't have a, let's say, a kind of just fulfilling a bottom line. Actually, we're trying to go to a upper limit or a lower limit, yeah. So these are the two difference between constraints and objectives. And here I'm going to show you how do we do this comparison. So once you have identified your constraints and objectives from your design requirements, we need to move to the second step. And the second step is basically so-called screening. Yeah. So we will be easily to translate or to just compare the constraints. So all of these constraints with a certain material data property. Yeah. So for example, if we want to say if it's water resistance, then we know if it's yes or no. If we need to be stiff enough, we know, okay, we need to have a high modulus to a certain level. Yeah, basically this is so-called screening. So by screening all these properties, we can already get our selection domain smaller. Yeah, but this is not enough, right? Then we move to the second point is so-called ranking. Sorry, the third step is so-called ranking. Yeah, the ranking is basically a procedure corresponding to objectives. Yeah. So after screening, we have already a bunch of materials that are fulfilling this kind of minimal constraints or minimal requirements of the material. So yes or no thing, basically. And then we try to use a certain criterion to select further. Yeah, so these are the kind of optimization part. As it is about optimization, so we will have a bunch of materials and we need to rank them. Yeah, and then you would say, you will be able to see which one is the best and which one is the one that does not fulfill your objectives so good. Yeah. And after this ranking procedure, basically you already know which material is your best option. Yeah, because you have the ranking. Yeah. The ranking can be displayed in different ways. I will show you in detail later. And the last step is so-called documentation. So basically now you have already the selection of materials available, and you just write a nice documentation to tell how you apply the tools, the concepts of your selection. All right, and then you're gonna do the final selection, of course. Yeah. So now I'm gonna give you those 4 steps, yeah, just to recall: translation, yeah, screening, ranking, and documentation step by step. Yeah. Most importantly, first 3 steps, and among them, most important in the ranking step. Yeah. So first, let's start with translation. So translation is actually important, as you can see, because this is the predictor of everything. If you did a wrong translation, your material selection will be most likely not correct. Well, so what is translation? Basically, translation is to express design requirements as constraints and objectives. How do we do that? Actually, that's pretty easy. What you need to do is basically just list the functions of your product. Yeah, the functions of the material in your product should fulfill. And then you will be easily see what are the constraints and objectives. Yeah. For example, here we're asking the question, what essential conditions must your material meet or must your product meet? Yeah. So here I'm giving you again a few examples just to be inspired. From the book, you will find many more. Yeah. And after these constraints are defined, and then you try to ask what are the objectives. Yeah. So the objectives are related to some measures of performance. Yeah. So how could we maximize or minimize the performance measure? Yeah. Typically, they are related to mass, yeah, volume, eco impact, or cost. Yeah. So for mass, we're always, yeah, for most of the cases, 99%, we're pursuing lighter, the lighter the better. Yeah. And the same applies to cost. Yeah. So it's also the cheaper the better. Yeah. And after the constraints are done, we're gonna do basically to do the screening. Yeah, screening is something pretty easy to do, so I'm not gonna explain you in detail. And now we're gonna just go to the ranking part. So how do we do the ranking? Yeah, as we said, we need to have a measure of the performance. Yeah, how do we identify or define this measure of performance? We said as light as possible, as cheap as possible. Okay, that's just a rather concept. To do the optimization, we always need a const function. Yeah. So this kind of measure of excellence or measure of the performance is so-called material index. Yeah. And this index can be a, let's say, single material property. For example, tensile strength. Yeah, you want to get a material, yeah, as strong as possible. Yeah, it's not just to fulfill a bottom level of strength, but you want to have it as strong as possible. Yeah, then the strength is becoming a material index. It's becoming objective. Yeah, because you want to optimize it. Yeah, and it could be also a group of material properties. Yeah, as we have already said during the first week lecture, and it could be the modulus over density. Yeah, so the specific modulus, E over rho. Yeah, this is actually the most, well, one of the most used material index. And all of them could be used to do basically the selection of materials. Yeah, so to maximize the performance, we have two steps to do. So first, apply all the constraints. Yeah, then you have already a limited selection of material, and then you use the basically material index to optimize. So there's two steps. Here, I'm going to give you some examples to show you how to do this kind of. In the end, it's about ranking. Yeah, but here I'm going to show you how firstly we derive the so-called material index, and then how do we do the ranking. Yeah, this is a very simple basically material index. Yeah, because it's a one property. The product we're here talking about is this cover of the helmet. Yeah, for a motorcycle or anything. So you can see that the design requirements are easy. So we have two constraints, basically. First, this cover has to be transparent, yeah, for the driver to be able to see. Yeah. The second, it should be able to be molded. Yeah. So that's related to processes a little bit later. And the more important thing is we need to identify the objective. Yeah. So we could have two, let's say, objectives, but first I'm gonna show you the first one is as tough as possible. Yeah, because it should fulfill the requirements to protect the driver or the visitor. Yeah, and that means we should maximize the fracture toughness, the K1C. Yeah. So if you're not familiar with this concept, so try to visit the book and visit other materials to learn what is K1C about. It's related to the fracture toughness. And then the material index is basically just we choose our materials with the largest K1C. And then we do the ranking, and then you know which one is the best one. And an alternative objective could be as cheap as possible. So that is easy. We're going to minimize the material cost. So this is the CM. Yeah, you could find this in the software, and it's going to be choose the material with the smallest one. All right, that was really a very simple example to show you how this kind of material index works and how you could really apply this to your design process. And here I'm going to show you a few more examples that they're all related with minimizing weight design. Yeah, and they're all related with a group of material indices. Yeah, so here the very good example is an airplane. Yeah, because this kind of component really involving many structures that are kind of characterized by different, let's say, mechanical requirements. Just taking a few examples, for example, for this, basically for this rod here, yeah, the requirement for this is it should be as strong as possible. So we should have it is subject to tensile loading, and we should aim for a specific yield strength. Yeah. While for this part, the spar of this airplane, the loading mode for this is bending. Yeah. So the most important loading mode for engineering structures is a bending, and even it's a beam bending in a way. And so here, the kind of material index is this square root modulus over rho density. So there are also few. So you are probably wondering how these are derived. And here I'm going to show you two examples, basically, to tell you how the material index for these cases are derived. The first is this tensile load. Yeah, so you can imagine this is a rod, and it is subject to a certain tensile force, and we have a fixed length of it, and basically your constraint here is the length is specified, and the other is basically the material should not fill under load F. Yeah? And our objective is to get minimum mass. Yeah. So how do we do the constraints, and more importantly, do the objective? Yeah. So the two constraints are clear, and you can just write the equation for the second constraint. So we say it shall not fill under certain load F, meaning the material, because F is something related to the geometry. Yeah, we want to get something related to the material. So we just use this F divided by the area A. We have already, this is the strength. Yeah, that means the material strength, the required material yield strength has to be bigger than a certain value. Yeah. That is constraint, and the objective is minimum mass. So here is the M. M can be easily translated to, in such equation. So A times L times rho density. So if we want to minimize M, basically we should minimize this stuff. Yeah. So here rho is a constant, L is a constant. The only kind of variable is A. So where do you find the A? Yeah, actually A is here. So if you now just take the A from this constraint equation to our objective equation, you can easily say we will have the M as our minimized quantity to just written in such a way. Yeah. So here M is equal to F times L and times rho over sigma y. Yeah. So these two, as you know, they're all fixed numbers. Yeah. If we want to minimize M, basically we need to minimize rho over sigma y. In other words, yeah, we need to maximize the sigma y over rho, right? So we tend to use kind of maximize, because that will be easier to be overviewed in the software or in the diagram. Yeah, that's why we didn't go with the minimum, but we go with the maximum. Yeah. So we identify our material index, the capital M, yeah, as the sigma y over rho. And we want to maximize this sigma M, maximize this material index. Yeah. All right, I think that's a general flow how this is derived for tensile load. Here I'm actually going to show you a little bit faster how the bending stiffness or the material index for beam bending is derived under the objective to minimize mass. So the concept is exactly the same. Yeah, here you need to familiar yourself with how this, for example, this equation is written. Yeah, because before we were talking about the tensile strength, that was relatively easy. So here we're talking about the bending stiffness. Yeah, when you talk about bending stiffness, you need to involve a few more quantities. For example, like this second moment of area, because this is the way you can really express your bending stiffness with the geometry, yeah, and also with your material parameter, which is this E modular, yeah. Basically, we still do this. So we replace the geometry features into this mass equation, and finally you arrive in such equation. So all of this are basically constants. Yeah. If you want to get more details, just try to follow the book. You can get it quite well. And the only variable is this term. So we want to minimize the mass, meaning we want to minimize this term. So rho over square root of E. Once again, we prefer to have maximum than minimum. So we just use the capital M expressed as the square root of E over rho. Yeah, this is how they basically the bending material index was derived. This is very useful. You actually, once you learn how this is derived, you could apply this to so many components, so many structures to choose your materials. Yeah. Of course, if you're having different loading moment or loading mode, yeah, you have to learn the way, basically the methodology is shown here, to do the derivation. All right. So the last step is after you get your material index and you also apply the constraints, you limit your selection group. Now you want to meet the objective and you want to do the ranking. There are a few ways to do the ranking. Basically, you can just rank them, right? If you have your material index and you can just rank them in a table, then you just pick the, let's say, the top one after you apply the constraints. You just pick top one and that's your material, right? But that's a little bit boring. It's not so straightforward. So here I'm showing you how to use the charts to do a ranking, basically how to use the Ashby diagram to do ranking. So this involves a little bit manipulation of your equations. So we just take example of a light and stiff beam. Yeah, so this is basically what we studied before. The material index, you know already. This is the square root of modulus over rho. We try to do a little bit of rearrangement. You can see we just move the M to right and the modular to the left. And we for both sides of the equation, we take logs. Yeah? So you can see now this multiplication becomes plus. Yeah? And the relation between modulus and density is becoming linear. So we're talking about the log scale. Yeah. So the log E is in a linear relationship with the log rho, n plus a constant. This constant involves the material index M. Yeah. And of course, the kind of slope is 2. And if you just now try to recall the Ashby diagram or the material property diagram. So we go with the x-axis as density and y-axis as modulus. If you remember what we said last time, actually the axes are always in log scales. Yeah, that means if we just try to plot this equation into this chart, you actually get it as a line. Yeah, so I hope everybody can reflect this. And the slope of this line is 2, basically. Yeah. And if we want to have a maximum or a largest m possible, meaning we're just pushing this line towards the top left corner, right? So the line with the most top left corner has the maximum or largest m. Yeah, that's how you're gonna do the selection or ranking visually, basically. Yeah, and so here there are also a few more equations if you are in different loading mode. Yeah, so here I'm giving you the beam bending. All right, and this is basically the principle. Yeah, how you can do it. And here I'm showing you another way to do it. So that one was by software, and you are going to do it also by software. And actually, what you can do this is basically also by just a print out chart of this bubble chart. If you have such a just a chart with you, for example, you are once again are asked to choose a light stiff beam, and basically you're going to do this. You're going to use this this different lines listed here to choose your materials. For example, here, if you can look at this one, this is the modulus over density, and you can go up to a certain level. And what you should be noticing for interesting fact is, for example, here we're looking at steel, and here we're looking at aluminum alloys. So they are usually competitors in the market. But roughly speaking, the densities of these two materials are so different, as well as the stiffness. Yeah, but actually their specific stiffness, basically E over rho, is almost the same. Yeah, very interesting. And you might get a question, yeah, related to this point. If we just recall the airplane, you see when we just talk about the spar, everybody knows many of them are used by composite materials, but you know there are also aluminum alloys could be applied, but we never see basically steels applying in the airplane components. Yeah, so given the fact that the kind of specific stiffness of steels and aluminums are so similar. Yeah. If you just ask yourself this question, I don't know if you could get an answer. Yeah. Actually, I'm already giving hint of this answer. Basically, most of the loading components in an airplane will be subject to bending. Yeah, that's why, especially beam bending. Yeah, that's why we cannot do the material selection via specific stiffness, but we have to go with this square root E over rho. Basically, the slope should be 2 instead of 1. If you just go with this kind of slope as 2, you can clearly see if we push up a little bit more. So here is the aluminum, but steel is far behind aluminum in that sense. Yeah. Well, that's just a nice example for you to realize how powerful this kind of visualization of your objective in a bubble chart. And of course, after you just push this line to a certain limit, you will have just a few materials left. You can already pick them up, of course, if you want to be more careful. And you can also just list them and you rank them again. Yeah, you will see the material with the largest material index and the second one, and so on. And that's basically everything I would like to tell for this kind of appetizer for you to get some deep learning in task 1 and in this chapters 3, 4, 5 of the book. All right, so I wish you good luck with the study, and see you next week at the seminar and also at the flipped classroom.